Good morning. I'm Dr. Samir Usman Bhagwan. I'm working as assistant professor at Dnyanshree Institute of Engineering and Technology, Department of Electrical Engineering. So today I'm here to deliver the topic symmetrical components. In that, we are starting with its objective and then we'll discuss its outcome. So for this topic, we have framed the course objectives such as to study the symmetrical component theory and its application to analyze symmetrical fault in power system. Okay? And after learning this particular topic, my student will be able to get something, that is what they will be able to apply symmetrical component theory to star connected loads, transmission lines, synchronous machines and transformers to compute performance parameters. Okay? So, as we know that there are different kinds of network elements are there in the power system, such as generators, then transformers, then transmission lines, loads. In that, these all four elements are playing their important role, such as the role of generator is to generate the power, then role of transformer is to transfer the power from one circuit to another circuit by stepping up the voltages and by keeping the power constant. And the role of the transmission line is to transmit the power, and fourth one is load. That is ultimate thing which we are getting connected at the receiving end of the system. So with this, we have to first of all understand there are several situations which took place in the power network, such as balance as well as unbalance. There are two situations we need to understand. What is balance situation? Means what? If the system is having the same load connected at each and every phase, then definitely the current carried by each and every phase will be same. But that situation may not arise every time, right? Situation is always vice versa. Situation is always, what I can say, unbalanced. The system current is always unbalanced, and which causes the unbalanced voltages also, because we don't have any control on the utility, our customers. Means what? The way they are switching the components, they are switching the devices, that is not in the control of, what I can say, power generating company. So that's what we need to understand this particular mechanism very importantly, right? Means what? We need to understand if such kind of things are taking place, right? What causes the unbalanced situation then? There are two situations which mainly causes the unbalancing in the power network. One is what? Unbalanced load, and second one is the faults, unbalanced faults. What are the unbalanced loading situation? If we are loading the R phase, Y phase and B phase independently with a certain load which is not at all same, then definitely it causes the unbalancing. Suppose the R phase current is carrying say 10 ampere, other one is say 5 ampere, third one is say 20 ampere. This situation we can call it as unbalanced loading condition. Second thing is what? Fault condition. In that fault condition, there are several type of fault we know, such as series faults as well as shunt type of fault. In the series fault, we know that there is one conductor open fault, two conductor open fault, and in the shunt faults, there are several types, that is symmetrical fault and unsymmetrical fault. In the symmetrical fault, we know that there is a, what I can say, symmetrical fault. I'll write here. Symmetrical faults such as triple L fault, and second one is triple LG fault. In unsymmetrical fault, there are several categories: line to ground fault, then line to line fault, and third one is double line to ground fault. In symmetrical fault, we know these are balanced fault, means what the impact after its occurrence is same. So the fault current will be same in all the phases, while in case of unsymmetrical fault, there are several types: line to ground fault, line to line fault, double line to ground fault. So here the impact is different, right? Means what? The phase which is under fault, only that phase carries the fault current. Remaining two phases will not carry any fault current, right? So here the unbalancing is occurring, right? Second situation is line to line fault. It means that two phases under fault, right? It means that two phases are carrying the fault current. Third phase is okay, it's normal. So in that case, it creates an unbalanced situation. And third one is two line or double line to ground fault. It means two lines are falling on ground. In such a situation, also it creates the unbalancing. Now it's very important to understand how this particular system parameter will behave and how the protective system should be in place to work under such condition, right? So it's a very important role of power system engineers to understand this particular theory, and that's what this particular topic we have in our course, that is symmetrical components. So in the symmetrical components, one of the important scientists whose name is Fortescue, he has said one theory that if there are n number of phasors present in the system, then it can be resolved into n minus 1 balanced set of phasors and one zero sequence set of phasors. In that, n minus 1 means what? Suppose n I am considering here, n minus 1, I said n is nothing but number of phases. Number of phases can be resolved into, as per his statement, can be resolved into n minus 1 balance sets and one zero sequence set. One zero sequence set. Now here suppose I am considering n is equal to 3. Suppose I am considering n is equal to 3. Now in this case, the n minus 1 will be equal to what? 2, and here 1. So 2 means what? 1 is positive sequence and another one is negative sequence. Okay, so these are the two sets we are resolving. They are having equal magnitude of their phasors, equal magnitude, but their sequence is opposite. The positive sequence is having the same phase sequence as the generator is having in the winding, while the negative sequence is having the exactly opposite phase sequence which the generator winding is having, right? Suppose we are having the generator symmetrical winding in a phase sequence, say RYB. So here also we are expecting the phase sequence in the positive sequence as RYB. Oh, okay. Or in other way, we can say that suppose it is a ABC, then here also we are expecting ABC. What is happening in the case of negative sequence component? It is exactly vice versa. Suppose the generator is having the phase sequence RYB, then here also, here the phase sequence will be the RBY, or in the other word I can say, suppose the phase sequence is ABC, then here it will be ACB. So here the phase sequence is differing, right? So it is very important thing to understand this particular theory. And one more is there, that is zero sequence set, which will be there in a system if there is a connection of this particular neutral to the ground. Okay, so let us understand what kind of connections will be preferred in the power network. We know that there are certain elements we are having, generators are there, transformers are there, transmission lines, loads are there. Generally, how they are connected? They are connected in the three way. First way we need to understand is what? Delta connection. Second way is star connection with neutral. Here the neutral is floating. Is what? Neutral is not at all connected to the ground. While third connection is star connection with neutral grounded. So there are two ways to provide the grounding to the neutral. Either it will be grounded solidly or it will be grounded through certain impedance. Grounding impedance I can say, ZG. So these are the two ways we can have a connection. Now it's important to understand the relevance of each and every sequence component. As I said, there are three sequence set we are producing: positive sequence, negative sequence, and zero sequence set. What are their properties? Okay, what are their significance? That we need to understand. Okay, so as I told, positive sequence component is present if the system is balanced. It means that the current in all the phases are same. The phasors are having the equal magnitude and they are dispersed from each other by 120 degree, the way I have shown here. Okay, phasors are having the equal magnitude and they are dispersed from each other by 120 degree. So this is what balanced system. What is happening in the case of negative sequence? The negative sequence component presence causes mainly because of unbalanced loading condition and as well as because of fault condition. These are the two conditions which causes the presence of negative sequence component and as well as zero sequence component. So what are their consequences? Let us discuss about first negative sequence component. If the negative sequence component is present in the network, it causes the heating of the equipment. Means what? If this particular component is present, then definitely causes heating of the equipment. You may experience what I can say, some warmness in the equipment than its expected limit, right? And also it causes losses in the power system, losses in the network, losses in that component. This is what the consequences of the negative sequence component. Let us discuss about zero sequence component. Again, the cause I said is same. That is what this particular sequence component is present if there is an unbalanced condition or if there is a fault condition. Okay, and under such condition, this particular sequence component consequence is what? First consequence is if it is present in the network, then it causes the over voltage of the system, as well as it draws more losses in the network, right? It creates the instability in the network. So these two situations are definitely creating the instability in the network. So we don't want to be there, these two components to be there in the system. But we know that scenario is like that only. If the practical scenario will understand, the practical scenario is the system is never balanced, it is always unbalanced, the load is always unbalanced, so their presence is always there. Okay, negative sequence as well as zero sequence. So after discussion of symmetrical component theory and its different three sets, let us apply this particular theory to first element, that is synchronous machine. So now I am going to discuss about sequence impedances and sequence networks of synchronous machine. Okay, so in that, first of all we will consider a case of three-phase synchronous generator with grounded neutral. Okay, so here I have drawn a case of synchronous generator where these three windings are dispersed from each other by 120 degree and their neutral is grounded through grounding impedance. Okay, so this is what the case we have considered. Now, how this particular sequence network can be drawn, how the sequence network of this generator can be drawn. Okay, so that we are going to see now. So here the first set I drawn is positive sequence set. You can see here positive sequence network. In that positive sequence network, as we understood that the positive sequence network is having the same phase shift as just like a generator is having, generator winding is having. Okay, so here we have drawn the sequence network having the diagram showing the Thevenin equivalent circuit in each and every branch, just like EA in series with Z1, EB in series with Z1, EC in series with Z1. They are dispersed from each other by 120 degree, and as we already discussed that for the presence of negative sequence and zero sequence, here there is no any relevance of these components, that's why they are not at all shown. And here the neutral is also not shown, and which is not at all shown, which is connected to the ground. It's a simple network which we have shown, which represents the balance condition, which represents the balance condition. So this is what the model we have drawn, which we can call it as a three-phase model, okay, where the voltage source is connected in series with the impedance. If we represent its single-phase model, how it look like? The single-phase model look like this: the voltage source in series with impedance. So voltage source is EA in series with its respective impedance, that is Z1. So as we know, 1 represent positive sequence, okay. So here it is a positive sequence impedance, and as well as we have shown here the positive sequence current, okay. And this particular voltage we need to determine, that is VA1. So how the equation can be written? So the equation can be written as VA1 is equal to, so I just want to walk from A point to reference bus, okay. So A point to reference bus. So what is coming in picture? So first of all, this particular drop is coming in picture, which is happening between, which is happening across Z1, okay. So what is the impedance of this particular, what I can say, positive sequence impedance is Z1. So what is the drop which is happening in the positive sequence impedance? The drop is minus Z1 into the respective current is IA1, and as we are approaching to the positive terminal of this EA, that plus can be added. So I can write plus EA, okay, or vice versa I can write it as VA1 is equal to EA minus Z1 IA1. So this is the equation we have for the positive sequence voltage, okay. Now talking about its reactances also, if I want to know what is the value of Z1, so Z1 is having the 3 values. First is what? JXD double dash, second one is say JXD dash, and third one is say J into XD, where double dash, XD double dash represent subtransient reactance, XD dash represent transient reactance, and XD represent synchronous reactance. So the presence of this particular reactance is for hardly 1 or 2 cycle. The presence of transient reactance is for another 3 to 4 cycles, and the presence of synchronous reactance is after that, right? So when the system is approaching to the synchronous state, steady state, that reactance is synchronous reactance, that is XD. So this is all about positive sequence set. If we resolve the another set, that is negative sequence set. Here in the negative sequence set, the voltage sources are not shown, only their respective impedances are shown. Because we know the generator always generate the positive sequence set of the voltages. It does not generate negative sequence or zero sequence voltages. That's why we have not shown here the voltages in the negative sequence set or negative sequence diagram. So here the negative sequence impedance is shown as a Z2. Everywhere you can see Z2, 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 okay. And the respective current of the phases are shown, such as IA2, then this is IB2, and this is IC2. So here number 2 represent negative sequence set. If we draw, this is a 3-phase model, okay. If we represent its single phase model, it look like this. How it is shown? The impedance, and across that the voltages are shown, that is VA2, okay. The impedance is obviously Z2, and what is the current? IA2, and this voltage VA2 is with reference to reference bus, right? With reference to A bus, it is the voltage between A bus and the reference bus. So if we write the equation, how the equation of the VA2 can be written? So VA2 equation will be nothing but, VA2 is nothing but, what is that? If we move from A point to reference point, okay, if we start walking from A point to reference point, what is coming in picture? The direction of the current is opposite, so that's why we have to write minus. And as the drop is across Z2, so that drop is nothing but Z2 into respective current is what? IA2. So this is what the value of voltage VA2. That is negative sequence voltage. And now the last one is zero sequence network, okay. How the zero sequence network is drawn? You can see here, the 3 reactances are shown, that is Z0G, then Z0G, Z0G. They are having the equal magnitude, no problem. Now one more reactance we have shown here is Zn. That is the reactance which is present between neutral and ground. Okay, so here the ground is shown, you can see. So whenever ground is involved, there will be presence of zero sequence component. Okay, and here also one thing we have to emphasize is that we have not shown the voltages. Why? Because I already said that the generator always generates the positive sequence set of the voltages. Now if you see this diagram, the respective currents are shown, IA0, IB0, IC0. These are nothing but the zero sequence current of the respective phases. Okay. Now, if you see this particular diagram, this is a three-phase model. If we want to represent it single phase model, how one can represent it? The representation is done like this. It is consisting of the two impedances. One is zero sequence impedance, which is between the ground and what I can say, that respective phase, and another one is neutral impedance. It is shown 3 times because that unbalanced current is always flowing through the neutral. Okay. So, rather than this, I can say that this neutral current is nothing but the summation of all these 3 sequence components, and which is obviously we have to represent in the diagram. So, what we have to show here, IA0 is there, that is zero sequence current, then Z0G is zero sequence impedance, and third one is neutral impedance. Now, we would like to write the equation for VA0. So, how to write the equation for VA0? So, VA0, again the same thing, we have to start walking from A to reference bus. So, what is coming in picture? First of all, the drop which is happening in Z0G can be represented as the current direction is reverse. So, it is minus Z0G into IA0. Okay. Next, one more drop is happening here. What is this? 3 times Zn. Okay. Again the current direction is reverse. So, minus 3 times Zn multiplied by IA0. Or in other way, we can write this equation as VA0 is equals to, take this particular IA0 and minus common. So, minus IA0 in bracket Z0G plus 3Zn. So, this will be nothing but the equation of zero sequence voltage of the synchronous machine. Zero sequence voltage of the synchronous machine. So, what I did, I just took this particular term common. I have written the 2 drop. First drop is between, it is across Z0G, and another drop is across Zn. So, while representing the equation, VA0 is equals to minus IA0 in bracket Z0G plus 3 times Zn. Okay. So, as and when we want to analyze the unbalanced situation or fault situation of the synchronous machine, we have to apply this particular diagrams. We need to draw this diagram. We need to analyze the network of consisting of the synchronous machine by applying this particular theory. Okay. With this, I hope that this topic is clear to you all. Thank you.